In this presentation, I will be talking about our work titled Measuring the Unfaithfulness of Concept-Based Explanations. Imagine we have a chest x-ray that we pass to a vision model which gives a diagnosis of pneumonia. We also attach a post-hoc explanation method to the vision model to generate an explanation. The explanation must faithfully explain how the vision model arrived at its diagnosis and also be interpretable to the doctor. However, interpretability and faithfulness usually come at a trade-off, since higher faithfulness usually involves a more complex explanation, which is harder to interpret. Interestingly, prior works have shown high faithfulness and interpretability, which led us to question their results. Upon doing so, we found that they used flawed faithfulness metrics. Let us look at prior faithfulness metrics. There are two kinds. First, we will start with deletion-based metrics. Deletion-based metrics delete a concept and then determine the impact of that deletion in the model's output space. Deletion is usually done in the image space. A higher delta in the output compared to the original prediction is used as a signal for higher faithfulness. Results from deletion-based methods are typically shown in a graph such as the one exemplified in the slide. Deletion-based methods have two main limitations. First, it's unclear how to actually do the deletion. Deletion is an ill-defined operation for traditional vision models. Should we really replace all these pixels with red? And if we do, should the model actually interpret this red box literally, or should it try to fill in the gaps like a human would? Second, off-manifold images may confound the deletion results. Notice that deletion results in unnatural-looking images, and these images may be off-manifold inputs for the model. An increase in the degradation may be a result, like in this delta, may be a result from the off-manifold input rather than actually having to do anything with the deleted concept. Due to these limitations, our work avoids using deletion-based metrics. Surrogate-based methods measure faithfulness differently. They take the intermediate embeddings, and from these embeddings they generate an explanation. The explanation is then mapped to the output space using a surrogate. The output from the surrogate is compared to the output from the original model to see how well the original output can be reproduced from the explanation. A faithful explanation has a low reconstruction error. Surrogate-based methods come with two main limitations. First, they often use complex nonlinear surrogates. These surrogates will capture hidden computations in order to properly map to the output space. And these hidden computations are something that an interpreter, like a doctor, is also expected to do when looking at the explanation. Thus, these nonlinear complex surrogates allow explanation methods to show their interpretable explanations and also report high faithfulness. The second limitation is that the error metric here is usually very narrow, and it usually is looking only at the top one predicted class and ignores errors on the remainder of the output distribution, even if they are significant. We find that both of these limitations are adjustable, which leads to our contributions. We make two contributions. First, we introduce surrogate faithfulness, or SURF, a faithfulness measure that addresses these limitations. Then, using SURF, we conduct the first comprehensive benchmark of previous concept-based explanation methods, and we find that state-of-the-art methods that are previously thought to be faithful are not. SURF has two parts, the surrogate and the metrics. We start with the surrogate. A vision model for object classification typically has a feature extractor to obtain embeddings H, which go through an FC layer to obtain the logits. Each classification vector in the FC layer can be decomposed into a direction and a magnitude. Notice that any U-CBEM outputs k concept activation vectors, which are analogous to our directions, and their class-wise concept importances, which can be interpreted as magnitudes. In a similar spirit to the original FC layer, the SURF surrogate for any class index j projects the embedding into the concept space and takes a dot product with class J's concept importances to obtain class J's logit score. SURF measures errors in both the logit and probability space. Logit errors are measured by mean absolute error, and probability errors are measured by Earth mover's distance. This results in error metrics that operate across the full output distribution and are easy for explanation developers to interpret. Our benchmark results for object classification on Caltech 101 show that current U-CBEMs have meaningful faithfulness errors. The best performing method, SAEs, have an EMD of 0.2. On average, 20% of the surrogate output distribution is incorrect compared to the original. SURF can be used as a selection criterion for the number of concepts in an explanation. Plateaus in faithfulness scores indicate a natural selection criterion for the number of concepts. Less concepts in an explanation is usually more interpretable, but it trades off with faithfulness, so we can use a SURF metrics to navigate this trade-off. Please view the paper for more details, and we have open sourced our code. Thank you for listening.